Hey, calculus fans, long time no see. Well, it's Wednesday, June 3rd, and I'm going to make a video today. I'm going to make a video tomorrow. I'm going to make a video Friday, maybe even Saturday too. So it's time to get moving, and we're going to get moving. We've done a lot already. We've done limits, and we've done limits that have radicals in them that we have to get rid of. And we've done one-sided limits, so we have a good concept of one-sided limits. And it turns out that one-sided limits do play a part sometimes in the computation of, quote, regular limits, end quote, where x can approach from either direction. And we're going to look at such an example right now. Okay, limit as x approaches 5. Now, what's the first thing that we always do? Don't we try plugging in? So let's do that. Well, we've been down this street before, division by 0. So our result is invalid. But we did the right thing, we plugged in first, but technically that's illegal, so sometimes we'll get an invalid result. And when we get an invalid result by plugging in, it's always going to be the same story. The result's invalid because we're dividing by 0. And we look at it and we know right away the result's invalid. So we did something illegal, but no harm done. We recognize what's wrong and we're able to fix it. So our next step. Plugging in doesn't work. Try canceling a common factor. No good? Really? Well, it turns out we haven't been down this street before. We've been down the street where we divide by 0. But this is sort of a left turn that we take off of that street. The dividing by 0 street, we take a left turn. And we're on the street now where we're dividing by 0, but the numerator is not 0. Think about it. In all of the other examples where we plugged in and we were dividing by 0, both the numerator and the denominator were 0. And the canceling strategy worked. We'd cancel that common 0 factor out of numerator and denominator, and then we'd plug in. But that strategy only works when both the numerator and the denominator are 0. And the reason is when both numerator and denominator are 0, both numerator and denominator have a common factor such that when we plug in the value that x approaches, that factor becomes 0. Well, here, the numerator is not 0. So whatever factor the denominator has that makes it 0 when we plug in 5 isn't in the numerator. So canceling doesn't work in this case. So the canceling trick only works when we get this when we plug in. And we didn't get this when we plugged in this time. Here, we have a non-zero numerator and a 0 denominator. Cancelling's not going to get us out of this trouble. So we go to plan C, or step 3. Okay, that's why we were so interested in one-sided limits. I see. In this particular kind of situation, where we have division by 0, but the numerator's not 0, we got to go to plan C, where we analyze the one-sided limits. So let's do that. Now, in light of what I just said, what I'm about to do next is going to look pretty strange. I can't cancel a common factor and compute the limit that way. But I'm going to take this one-sided limit and I'm going to factor the denominator anyway. I do have a reason for this. I'm not going to be able to do anything useful by canceling factors in numerator and denominator. But for some reason or other, I think it's going to be helpful if I factor the denominator anyway. I'm not going to cancel anything, but I think it's important that I factor the denominator when I do these one-sided limits. Now, let me ask you a question. As x gets closer and closer to 5, what happens to x squared? As x gets closer and closer to 5, doesn't x squared get closer and closer to 25? It does, doesn't it? And so as x gets closer and closer to 5, x squared plus 2 is going to be about 27. Now, x never actually equals 5, so the numerator won't actually become equal to 27 in this case. But the numerator is going to get so close to 27 that we won't be able to tell the difference. It's almost 27, maybe a half a molecule less than 27, or a quarter of a molecule greater than 27. It won't be a difference that we can perceive with the naked eye, okay? As far as we're concerned, as x gets closer and closer to 5, the numerator looks like 27. So that's what I'm going to write. Similarly, as x gets closer and closer to 5, what happens to x plus 5? Isn't x plus 5 going to be really close to 10? It's going to be so close to 10 that we won't be able to tell the difference between x plus 5 and 10. So I'm going to write a 10 here for this first factor. And now this factor here, this is the troublemaker. This is the factor that becomes 0 when we plug in x equals 5. So as x approaches 5, this factor is going to get really, really close to 0. But it's not going to equal 0. Now, if I continued in the same fashion that I did for the numerator and for this factor, I'd just write 0 here for that factor. But I'm not going to do that because, first of all, this factor never actually becomes 0 because x never actually becomes equal to 5. And secondly, if I put a 0 here, I'm dividing by 0, and I can't do that. But somehow I want to represent this factor as something that's really, really, really close to 0. And I can't write 0 because then I'll be saying I'm dividing by 0. And 2, it would be a kind of a lie for me to put 0 here because since x never actually becomes equal to 5, x minus 5 never actually becomes equal to 0. But it gets close. It gets really, really, really close. And I'm going to signify that by writing this thing. This is epsilon. And by convention in math, epsilon is used almost exclusively to represent minute positive numbers, and maybe even minute positive numbers that are getting closer and closer to 0. So I put an epsilon there. Now there's one other thing that I need to make sure of. As x approaches 5 from the left, is this factor x minus 5 going to approach 0 through positive values or negative values? Well, here's how I figure that out. If x approaches 5 from the left, then x is to the left of 5. So here's 5 on the number line, and here's x. So x is to the left of 5 on the number line. So x must be less than 5. Now, remember what I was trying to do? I'm trying to figure out, as x approaches 5 from the left, does this factor approach 0 through positive values or negative values? This inequality doesn't tell me. So I want to rewrite the inequality so that it tells me something about x minus 5. So how can I get this inequality to tell me something about x minus 5? Can't I just subtract 5 from both sides, and then the left side will be x minus 5? And I'll explain the significance of this arrow in a second. Well, here, this says that x minus 5 is negative as x approaches 5 from the left. Okay. So I need to put a negative epsilon here. To denote that this factor x minus 5 is negative. And now I'll rewrite this as 27 over 10 over negative epsilon. Let me ask you something. Positive number divided by negative number, what do we get? Negative? So I'll write down my negative sign. And then the next thing I have to figure out is this. What happens if I divide a big number, 27 over 10, by something tiny? Big number divided by little number. Well, let's see. Let me take a big number like 10 and divide it by, let's see, tens, hundreds, thousands, 10,000s. 10 divided by 1/10,000. In fraction form, that's 10 over 1 over 10,000. And how do I divide by a fraction? Don't I invert and multiply? Okay, I divided a big number by a little number, and I got something much, much bigger. So the lesson is this. Big number divided by little number is a big number. And this little number is getting smaller all the time. It's approaching 0. So the big number I get when I divide this big number by this little number is getting bigger all the time. It's getting bigger and bigger and bigger. It's getting infinitely large in size, so I'm going to put infinity here. Now, step 3 is analyze the one-sided limits, plural. So I analyze the limit as x approaches 5 from the left. I've got to analyze the limit as x approaches 5 from the right. But before I do, let me just explain some things here that I will probably forget to talk about if I don't talk about them right now. This thing, I use it all the time. This arrow here, this is the universally accepted mathematical notation for the word implies or the expression this implies. So whenever we see this arrow, we think implies or this implies. So x approaches 5 from the left implies x is to the left of 5 on the number line. That implies that x is less than 5. That implies that x minus 5 is less than 0. So I've explained this symbol, and usually I don't make such a big deal out of these things, but I use this symbol more in the course of a day than I breathe in and out, okay? I use it a lot. We're going to see it, so I want to explain it. Second thing, if we're computing a limit and we got big number over little number, that thing's going to go to infinity. Now, some of us don't have a problem reasoning that out. Others of us don't have a problem reasoning that sort of thing out until we get in a test. And then we just sort of draw a blank, and we even need somebody to tell us what our name is. And if that's you, don't feel ashamed. I've been in that situation a few times myself. So we just sort of remember, if we're computing a limit, and our limit is of the form big number over little number, that thing's going to infinity. And if we have a negative sign out in front, then it's going to go to negative infinity, which means that it's getting infinitely large, but in the negative direction. Now, there's one other thing that I did up here that you may still be scratching your heads about. You may have seen me do this and you said to yourself, how can he do that? And this is what I did that may be causing you some consternation. This thing right here, this manipulation. Well, I'll tell you what. I'm going to state an obvious fact, but it's a fact that nobody ever thinks of, and I put myself in that category. When we have an equation, that's a two-way street. Usually we see an equation and we always read it from left to right, but we can read it from right to left also. So let's do that in this case, just to show that these two things are the same. Let's take 27 over 10 over negative epsilon. Now, if we divide by a number, isn't that the same as multiplying by its reciprocal? So in other words, this is going to be 27 over 10 times the reciprocal of negative epsilon. See, dividing by negative epsilon, same thing as multiplying by its reciprocal. And now when we multiply this out, don't we multiply across the top? And don't we multiply across the bottom? Well, the point is, 27 over 10 divided by negative epsilon is the same as 27 over 10 times negative epsilon. But this is an equation. It's a two-way street. So we can also go this direction. We can also go right to left. And so it's also true that 27 divided by 10 times negative epsilon is the same as 27 over 10 quantity divided by negative epsilon. So that's how I'll justify that. Now, where was I? I was saying step 3 is to analyze the one-sided limits, plural. So I've got to do the limit as x approaches from the right as well. And again, I factor the denominator, even though I know that I'm not going to be able to cancel. Or if I can cancel, it's not going to solve the problem for me. But I factor the denominator for a different reason. And I apply the same logic I applied before. As x gets arbitrarily close to 5, then x squared is going to look like 25, right? And as x gets arbitrarily close to 5, x squared plus 2 is going to look like 27. For all practical purposes, that's what the numerator is as x approaches 5. And as x approaches 5, x plus 5 is going to look like 10. And as x approaches 5, x minus 5 is going to approach 0. But it never gets there because x never actually becomes equal to 5. But this is going to get arbitrarily close to 0. It's going to get closer and closer to 0, but it's never going to get there. So what do we write to denote this factor? Epsilon, right? And now I also want to make sure I have the sign right. As x approaches 5 from the right, does x minus 5 approach 0 through positive or negative values? I need to know that. So let's see, if x approaches 5 from the right, then x is to the right of 5 on the number line. So here's 5, and here's x. So x is to the right of 5 on the number line. That means that x is greater than 5. But I don't really want to know about x. I want to know about x minus 5. So how do I turn this inequality into an inequality that tells me about x minus 5? Don't I subtract 5 from both sides? And when I do, I have the information that I needed. As x approaches 5 from the right, x minus 5 is positive. So x minus 5 is going to approach 0 through positive values. So I'm going to put a plus epsilon right here. And now notice what I have. 27 over 10 divided by plus epsilon. First things first, I have positive divided by positive. What am I going to get? Positive, right? Next, I have big number divided by little number, and this little number is going to 0. So big number divided by little number, that thing's going to go to infinity. Okay, I did the one-sided limits. And I can't emphasize enough that factoring the denominator is important in this exercise, and it's going to be increasingly important when we get to graphing functions. So please do this the way that I did it. Am I done? Let's see. What did we start out doing here? Didn't we want to know the limit of this function as x approached 5 from either direction? That we wanted, quote, the limit, end quote, as x approaches 5 from either direction of this function. So what insight have we gained by doing the one-sided limits? And think back. What relationship do the one-sided limits have to this thing that we call, quote, the limit, end quote, where x can approach from either direction? What's the limit? What's the connection between the one-sided limits and this thing that we call, quote, the limit, where x can approach from either direction? There's an important relationship between them. Do you remember what it is? Quote, the limit as x approaches from either direction exists exactly when the two one-sided limits are equal. So what did we say happened when the two one-sided limits weren't equal, like in this case? If the two one-sided limits are not equal, what can we say about, quote, the limit, end quote? What did we say the other day? We said that, quote, the limit, end quote, does not exist, right? That's what we said. So let me denote that up here first. the one-sided limits aren't equal, that means that, quote, the limit, end quote, does not exist. So there's our answer. And if we have an exercise like this in the text and we look up the answer in the back of the book, they're probably going to have that for the answer. Does not exist. Now, let me address a hypothetical situation. It turned out that the two limits, the two one-sided limits, were not equal. What would have happened if the two one-sided limits had been equal? So suppose that the two limits had been equal. They were both equal to infinity. What would that have meant? If both of the one-sided limits had been positive infinity, then, quote, the limit, end quote, as x approaches 5 from either direction, would have been infinity also. And by the way, since infinity is not really a point on the real number line, how do we really interpret this statement? This is what the statement, the limit as x approaches 5 of f of x equals infinity. It means as x gets arbitrarily close to 5 from either direction, f of x gets large without bound in the positive direction. That's what that means. Now suppose that the two one-sided limits had been equal, but they both equaled negative infinity. So another example. Let's suppose that the limits were equal, but they were both equal to negative infinity. In that case, the limit as x approaches 5 from either direction would have been negative infinity. And here's how we interpret that. Limit as x approaches 5 of f of x equals negative infinity means that as x gets arbitrarily close to 5 from either direction, f of x gets large without bound in the negative direction. Okay, that's our lecture for today. We will have one for tomorrow. I think I will probably wait until tomorrow to assign homework after we do tomorrow's lecture.